Okay, this feels like a good time for a summary. Gauss's law states that the net electric flux through any closed surface is given by the integral of the electric field over the area of that surface, and it's also given by the net charge enclosed by that surface divided by the permittivity of free space epsilon naught. Some comments on this is that Gauss's law applies to any closed surface. So it has to be a solid closed sphere or a solid closed cylinder or a solid closed cube. It can't be just an open surface. Um, each of the symbols, what do they mean? Well, the net electric flux, that's our symbol phi. E is the electric field due to the charge inside. The area of the Gaussian surface is A, and dA is a small element of that area. A and E are both vectors, and the charge within the closed surface is Q with an ENCL on the bottom for enclosed. Epsilon naught is the permittivity of free space, 8.85 times 10 to the minus 12 meters squared over newtons times coulombs squared. The net flux through a surface containing charge enclosed is independent of the size of the surface, the shape of the surface, and the position of the charge within the surface. All that matters is that it's actually inside. And then Gaussian surfaces are arbitrary, so we get to pick them. We can make them any shape we want, and they're imaginary. They don't have to be real. You don't have to get out a real cardboard box to make a cubed Gaussian surface. We choose a Gaussian surface for convenience to make this integral easy to do. So we get to pick the shape, which is good. And in general, we'll always pick a shape that's symmetric with whatever object we're talking about. Then as a reminder, a Gaussian surface is a closed surface that we use in Gauss's law calculations. That's a real quick recap of what we've been talking about here. Let's quickly do some examples now. We have a figure showing the electric field around a dipole. Remember, a dipole is just two little equal and opposite charges separated by a small distance. So we have a charge negative Q right here, a charge positive Q right here, and they're kind of close together. We're asked to find the net electric flux through each of the surfaces A, B, C, and D. So let's start with A. A is a sphere centered around positive Q charge right here. So our net electric flux we can calculate in two ways. We can do the integral of E dot dA, or we can do Q enclosed over epsilon naught. You're allowed to pick either method. I could do E dot dA, but that looks a little bit tricky because my electric field is not exactly uniform. It's affected by this negative charge over here. So to me, doing an integral of E dot dA looks kind of hard. I'm going to do Q enclosed over epsilon naught instead. So my Q enclosed is whatever charge is inside my circle A. The only thing inside my circle A is my positive charge plus Q. Minus Q doesn't count because it's outside. So plus Q over epsilon naught. How about the electric flux through surface B? So here's my surface B. It's over here. I'm going to use my same form for finding my flux. I'm going to use Q enclosed over epsilon naught because the electric field looks kind of odd. I think that integral would be hard to do. So my Q enclosed is just minus Q, and that's over epsilon naught. So there's surface B done. Next, what about the net electric flux through surface C? So surface C is this big outer purple one. So this one maybe is a little bit hard to figure out. You can look at the electric field lines. We'll write down Gauss's law. It's the integral of E dot dA equals Q enclosed over epsilon naught. I think E dot dA, that would be really hard to do because the electric field is variable and our surface shape is kind of like a kidney bean, and I don't know how to do the integral of a kidney bean. So I'm going to stick with my flux is Q enclosed over epsilon naught. So Q enclosed means how much charge is inside my kidney bean. So my charge minus Q is inside and my charge plus Q is inside. I have to add those together. Minus Q plus Q over epsilon naught. That gives me 0. And that kind of matches what we see For every line we see coming in, so let's take this one. For every line we see coming in, there was a line going out. So this one goes out, this one goes in. That one goes out, that one goes in. Out, in, out, in. For every line going out, there's also one going in, which confirms that the net electric flux would be 0. Last is surface D. So let's use our Gauss's law again. Net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. Again, we could do the integral. That looks hard to do. Kind of got a boomerang shape for D there. So let's do the Q enclosed over epsilon naught. Let's look at that golden color shape D. How much charge is inside there? I've got to say there's absolutely no charge inside there. There's nothing inside surface D. So there's no charge inside, so my net flux is 0. That matches what the picture looks like. Every line going in is also going back out. In this example, we have a charge of 170 microcoulombs, and it's at the center of a cube of edge 80 centimeters. No other charges are nearby. Part A, draw the electric field of the point charge. So I'm going to put my point charge in the middle of the cube. I don't draw 3D all that well, so I'll try and get it at the center. I think that's close, maybe, hopefully. Okay, we'd like to draw the electric field. What we know is that electric field lines come radially outwards from a point charge. Now, these are coming out every way in 3 dimensions. That would be a nightmare for me to draw, so I'm just drawing those electric field lines in 2 dimensions. You can go ahead and try and imagine it. Probably you're a better artist than I am, so feel free to try and draw that in 3 dimensions if you want. Hopefully you can see that the electric field lines cut through all the faces of that box because it comes radially outwards in every direction, front, back, up and down, left and right. Okay, part A done. Part B, find the total flux through each face of the cube. That seems a little bit difficult. I'm going to go ahead and read part C. Find the flux through the whole surface of the cube. That one seems easier, so I'm going to do part C first. So I know my net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. When I do Gauss's law, I can calculate my flux 2 ways. I can do the integral of E dot dA, or I can do Q enclosed over epsilon naught. I should do whichever way is easier or whichever way is possible. Integral of E dot dA is definitely possible, but I've got a radial electric field cutting through planes, a cube. To me, that integral is hard. So my electric field varies as R, but my surface is in X, Y, and Z. That's a real toughie. I don't want to do that. But this one's pretty easy to do. I know my Q enclosed. It's 170 microcoulombs. So I'm going for the second way. So I'm going to say my net electric flux is Q enclosed over epsilon naught, 170 times 10 to the minus 6 coulombs, over 8.85 times 10 to the minus 12 meters squared over newtons coulombs squared. That gives me a net electric flux of 1.97 times 10 to the 7 newtons meters squared over coulombs. Okay, there's my net electric flux through the whole surface. Part C done. What about my net electric flux through each face? Here's where symmetry is real useful. So let's think about a cube. A cube has 6 faces. And our charge is at the center. That means everything is symmetric. The same number of lines will cut through each face. So that means my net electric flux through one face equals 1 over 6 times my total electric flux. So 1.97 times 10 to the 7 divided by 6, which will give me 0.320 times 10 to the 7 newtons meters squared over coulombs. Okay, part D. Would your answers to A and B change if the charge were not at the center? That's a good question, and I'll answer that on the next slide where I have a little more room for a diagram. For part D now, I'm going to abandon my three-dimensional drawing and I'm going to go to a two-dimensional drawing. So part D, here's where my charge is right at the center. Draw my electric field lines. They come radially outwards. Okay, I'm not really happy with this one, so I'll redo this one. So that's when my charge is at the center. What about if my charge is not at the center? I'm going to move my charge right over next to one side. Okay, my electric field lines actually won't change. They still have to come radially outwards. So at side. So for part A, the question, would my answers to not A and B, B and C, would my answers to B and C change? So for part B is how about the flux through each face? So flux is a number proportional to the number of lines entering or leaving a surface. So if it's at the center, we have this many lines going through a surface. If it's at the side, this is interesting. The lines are denser over here on the right than they are on the left. They are definitely not the same. So for part B, yes, it changes. So part B, if we were to calculate the flux through each side now, that would be much more difficult to do. In this case, we'd have to do the integral to find the flux through that face, and that would be a tough integral to do. Okay, how about part C, the flux through the entire surface? Maybe you know the answer to this one already because we did actually discuss it before. But when it's at the center, if we count the number of lines, we would see that we have 8 lines cutting through the entire surface. When it's at the side, we still have 8 lines. So if it's at part C, there's no change. So the net electric flux through the entire surface doesn't change as long as it's inside, but the flux through any one little bit of the surface could change. It's the total flux that doesn't change.